And next presentation is the computer simulation cleavage fracture surface morphologies in steel plates. Experience here.
My name is Taiko Aikawa. I'm a first-year student of the master course of the University of Tokyo. Today I will present my study, computer simulation of cleavage fracture surface morphologies in steel plate. Recently, as the structures using steel plates like container ships are becoming bigger, high-strength steel plates for these structures are becoming thicker. So the risk of brittle fracture is becoming higher. Brittle fracture abruptly initiates from a small flow and unstable propagates after initiation, leading to serious accidents. So control and arrest of crack propagating is important. It is well known that brittle fracture surfaces of steel plates exhibit irregularities with typical morphologies, like chevron markings and shear rips. The relationships between roughness of brittle fracture surfaces and arrest toughness is generally recognized. And it is said that shear rips reduce stress intensity factor by crack closure force acting on uncracked ligament. But the relationship between cleavage fracture surface morphologies and crack arrest toughness is not understood well. So manufacturers can adapt the effect of surface irregularities to the design of the steel plates. Our objection is developing numerical model for the reproduction of fracture surfaces and arrest lengths. This is the overview of the model. First, I explain flow of calculating K Kinoma. Look at the figure on the upper left. Split the crack front into microcells and of three orthogonal planes, 1, 0, 0 plane having the maximum normal stress cleavages, and calculate K1 tip, K2 tip, K3 tip for each cells. Using this and considering the effect of uncracked ligament and shear rips, finally calculate K Kinoma. This KQ normal is compared with KC local calculated from KCA. If KQ normal is bigger than KC local, crack propagates. If not, crack is arrested. This is the assumption of crack propagation. The model has two rules. First, only one cell crack propagates at each calculation step. Second, if crack propagates from multiple directions, select the cells with the highest K value. K1 tip, K2 tip, K3 tip is approximately calculated considering three effects. The effect of crack front edge being non-straightness, the effect of ridges between the cells, and the effect of crack surface being non-planar. First effect is considered by using the equation developed by Rice. Ridges between the cells decrease stress intensity factor at crack front. Third effect is considered by using the equation developed by Yao. Using K1 tip, K2 tip, K3 tip, the model calculates K Kinoma. This is the detailed equation calculating K Kinoma. This K Kinoma equation is based on the equation sigma n. Sigma n is the normal stress acting on the 100 plane at crack front. RC is the characteristic distance at which normal stress acts on the cells. Here is the equation calculating Kc local. Alpha K is constant. KCA RS toughness is calculated by the experimental formula using sharp impact test absorbed energy transition temperature. This graph shows the distribution of KCA corresponding to the change of temperature. Uncracked ligament carries crack closure pressure. The present study introduces crack closure effects into the model. Uncracked ligament splits into square cells and crack closure stress works on each cell. The amount of decreasing K value by each cell is summed finally. In the present model, suppression of brittle fracture is replaced with the increase in crack RS toughness as shown in this graph. Thus, K value is distributed along the thickness direction. From now, I explain the calculation to reproduce the fracture surface and crack RS toughness. Brittle fracture surface of temperature gradient test was subjected to the calculation. Plate thickness was 30 mm. Yield stress was 355 megapascal. The condition of the experiment is as follows. Applied stress was 300 megapascal. Temperature distribution in the plate width direction was shown by this graph. I use a 3D laser measurement system to capture 3D fracture morphologies. Mark A is the actual fracture surface. Mark B is the 3D surface. We can check the area. We can check the area of brittle fracture surface, shear lips, and uncracked ligament. Using the result of 3D measurement, I decided the parameters alpha K and F. F is the parameter deciding the area of uncracked ligament as this graph shows. The size of calculation cells is 1 mm multiplied by 1 mm by 1 mm. Mark A is a simulated fracture surface introducing crack closure effects on plate surface. Mark B did not introduce the effect. Please look at RS crack length on the table. The actual crack length was 302 mm, so the calculation introducing crack closure effects can reproduce crack RS length well. In terms of the surface morphologies and the form of the crack front, Mark A can reproduce well. This is another calculation result. The size of the cell is smaller than the before calculation. 0.5 mm multiplied by 0.5 mm by 0.5 mm. The actual brittle fracture surface has chevron markings propagating from plate inside to the plate surface. Simulated surface has the same tendency of chevron markings. From this result, we can clearly check that the model can reproduce chevron markings well. So the model can reproduce crack length and brittle fracture surface morphologies well. Next, I explain another calculation. The same testing condition as the reproductive calculation was applied, but sharply absorbed energy is changed as minus 50 degree, minus 75 degree, minus 100 degree. From this calculation, we intend to identify consistency of the present model. The calculation result is this figure. We can check that crack arrest length decreased as steel toughness increased. From this result, the model can reproduce actual crack propagation and arrest process together with fracture surface morphologies. So the model has the potential to use for understanding the relationship between crack arrest toughness and fracture surface. This is conclusion and future tasks. Numerical simulation model was developed to simulate brittle crack propagation by taking the effect of fracture surface irregularity, crack front non-straightness, and uncracked ligament into account. The model can reproduce crack arrest length and fracture surface morphologies well. Future tasks is validation of the model under various properties and testing conditions to use the present model for increasing arrest toughness of steels. This is appendix. That's all. Thank you for listening.